The dipole antenna, the most basic real-world antenna. We might build one of these during our break. Just two conductive equal length parts. A feed line connected in the middle, and there it is. Simple, simple. Easily constructed. The actual length is shorter than the free space length, so when you calculate it, the actual length will be a little shorter. But it depends on the physical size of the wire. Thicker will be shorter. The thicker also means a wider bandwidth, which is good. Proximity to nearby objects may affect it, like the ground, for instance. The closer you are to the ground, the shorter the antenna is going to be. So you start with 468 divided by frequency and trim for resonance. Remember 468? 2, 4, 6, 8. Who do we appreciate? 468 divided by frequency, and you got it. To increase the resonant frequency, you shorten it. With a central support and ends sloping to the ground, it's called an inverted V. So if we took this antenna and we pushed this up into the air on a mast and got these lowered down, you'd have an inverted V. By sloping it like that, you get a better match up here. It'll match to 50 ohms a little bit better. So there's one radiation pattern for the dipole. This is showing the horizontal pattern. You say you're looking down at the antenna. The antenna is oriented like this. You're looking down on it. The signal's going out in both directions, perpendicular to the wire.
Actually, 360 if you count vertical.
Yeah, right. This would be the wire going across this way, and it's putting out a signal all the way around. What happens is it gets squashed because you can't put it in free space. You can't get it up high enough. The ground reflects a lot of it, so it kind of balloons. And that's 2.15 dBK.
Also, the formula that he cited there for the lengths, that's going to be both lengths. So you're going to have your shield side and your center conductor.
Correct. That's
together.
the full half wave.
Both of them.
Yeah. So when you're taking that and cutting it in half. Does that make sense to everybody? Okay, and the gain is 2.15. Feed point impedance is approximately 72 ohms in free space. That's theoretical. That varies with the height above ground. If you can get the antenna more than a half wave above ground, you'll approximate that 72 ohms. But it also means the antenna is exactly horizontal. If you drop the ends, then that 72 ohms begins to drop as well. And
Then, if you install the same antenna in two different places, you'll find the match is different just because of what's going on around it. That's why you need an antenna analyzer or an SWR meter. Analyzer is better because you don't have to transmit. But
well, the analyzer, you don't need a transmitter with it. It's got a built-in micro transmitter, covers all the frequencies you need, and it's just a lot easier to do. You don't have to, fire up the transmitter and have coax go into the antenna. So, feed point impedance, approximately 72 ohms in free space, varies with height above ground, and varies with proximity to near objects, typically closer to 50 ohms in the real world. And at odd harmonics will be about the same as the impedance at the fundamental frequency. This is for a half wave antenna. So we look at the way the band plan is. 80 meters, 40 meters, 20 meters, 10 meters. Those are even harmonics. Why did they do that? Well, it's because back when amateur radio was developed, they weren't using coax. Coax hadn't been invented. They were using twin lead, like this stuff. And they were running out to an antenna that was a non-resonant antenna, and then using a tuner to make all it work. So back then, odd harmonics worked really well. I mean, even harmonics worked really well. If you were using a tuner, it would tune up that random length of wire better, 80, 40, 20, and 10. Made sense. So, a dipole. Quarter wave. On one side side and quarter wave on the other side, fed in the middle. And this is showing what happens to the voltage curve. Your voltage is highest right at the end of the antenna, and it's highest at this end. It's just the opposite.
And current is highest in the
And
middle.
current is highest right in the middle. That plays into how efficient your antenna is and what kinds of effects will be noticed when you have objects close to the end. So this is the ouchie end. You don't want to be touching that part of the antenna when you're transmitting.
That's where you put your hot dog when you want to cook.
Yeah, that's the high voltage end of the antenna. You get high current here, and that's where maximum radiation occurs. So think about it. You've got a vertical antenna mounted to the ground, and you've got your coax going right to the bottom of the vertical. You stand one of these up, and that's your vertical antenna. Your high current is now at ground level. Does that make sense? Well, that's convenient, and that's the easy way to do a vertical, but it doesn't really make a lot of sense the way the vertical radiates. So current distribution, highest current is right in the middle, and if you can get that high current point high, then you've got maximum radiation up high. That's where you want it.
That's your inverted V. basically.
Yeah, or a beam antenna, on a tower. That works the best. So vertical is with ground planes, one half of the dipole, the other half replaced with an electrical mirror called a ground plane. Ordinarily, an HF vertical would be mounted on the ground, and you'd have radials either buried or right on the surface of the ground, providing that reflective screen. The more the better. If you've got a VHF antenna, you might have that mounted on the roof or someplace up high. So you don't have the advantage of having a ground underneath it. A quarter wave antenna needs a ground plane. A half wave antenna doesn't, but a quarter wave antenna does. So you could use earth, a metal screen, mesh, a cookie sheet, Okay. So you calculate for dipole, half wavelength long. So the awkward part about a half wavelength vertical is that it's hard to feed it in the middle. Okay? You can't run the coax right down the side next to part of the driven element because it upsets the SWR big time. It won't work. Well, you can pull it off to the side horizontally, but that's awkward.
One thing you can do with an HT is take a piece of wire and hang it, screw it down to the frame of the
Make
radio.
another quarter wave.
You can actually increase the gain of the radio by quite a bit by doing that. It's called a tiger tail. Something to play with. If you're going to be in a sketchy area someplace, hiking or whatever, if you need that extra, you can do it. And all you got to do is attach it to the metal frame of the radio inside, snap the battery back on, and you'll have a lot higher gain with your radio. Simple.
So, okay, you got a matched quarter wave here. It's really not a quarter wave in length. Quarter wave would be 19 inches, but it's using this short antenna with a little coil in here to match it. And then the other side just goes to the case. It's using the case as the other half. Well, that's not resonant. So if you substitute a resonant wire, it's way more efficient. And same thing if you have an antenna on the car, you've got a quarter wave antenna mounted on a mag mount. It's using the car as the other half. Well, that's a little different because it's a ground plane. And the quarter wave ground plane is pretty efficient.
So Steve, I have a question. The tiger tail, would that have to be 19 inches then?
Yes.
Okay.
Yep. Or whatever works out for that size wire, it'll change with the size of the wire and with the type of insulation you've got on the wire. So you just play with it until it works. It helps to have an analyzer to do that, but you can do the same thing with an SWR meter, get the transmit, see what the SWR is. When it comes down to 1 to 1, you got it. So Quarter wavelength long is exactly half of the 468,234 divided by frequency, and then trim for resonance. Start off a little big. If you're making your own antenna, it's much easier to trim off than it is to stretch wire. And it's just showing some possibilities. Here's your ground plane. Here's an HF vertical with your ground underneath it. If you had something solid, like a big cookie sheet or a pizza pan works great. And of course, this is your half-wave dipole with your feet in the middle, but you can't bring it down the side. You've got to pull it off here, at least 19 inches on 2 meters. If it's HF, you're going to have to pull it way out. Keep it away from the antenna.
I got a fiberglass motorhome, and I siliconed a 24-inch piece of I think it's 16 gauge steel to the top of the motorhome, to mount the mag mount on, worked fine.
Yeah.
But a fiberglass body doesn't work.
Nope.
Neither does my aluminum.
Well, it'll work for the radio, but the magnet won't
The
stick.
magnet won't stay.
Hey, Steve, when you're pulling it off perpendicularly from the center,
How far?
Is it supposed to be about a quarter wavelength?
Quarter wavelength, yeah.
Okay.
So at 2 meters, it'd be about 19 inches.
Right.
But yeah, the lower your frequency, the longer it's going to have to be pulled out. So, ground plane. Feed point impedance about 35 ohms with horizontal radials, but if you lower those radials, you can get it down to about 50 ohms. So that means what? When you have quarter wave antenna mounted on the top of your car, it's not seeing 50 ohms. So how did they get it to 50 ohms? Well, they've got a little inductor in there, and they cheat. But they get it tuned so that on a car top it sees 50 ohms. So with ground plane verticals, that's what it looks like from the side. It goes up pretty high. So a typical handheld also has a little antenna. Yeah, the antenna is loaded to shorten the antenna, or not. I mean, so you can buy tactical fold-out antennas that are full 19 inches, and they are more effective. Another, adding, like you said, adding Tiger Trail helps. Right, if you're using it inside a vehicle, it obviously is being
that's
shielded by
yellow.
the vehicle. So something other people may not necessarily think about, if you're inside a vehicle and you're close to the window, it gets out pretty well. If you're in a bigger vehicle like a bus, those window openings need to be a half a wavelength. What's a half a wavelength of 2 meters? Well, that's like 3 some odd feet, 38 inches. Well, if the window opening isn't that big, you're not going to get much signal out. You get some, but it won't be very efficient. And going to 440 is actually easier to get that signal out through that little window than it is on 2 meters. So it may seem like 440 is going through the side of the building, or it's not. It's just easier to get out the window, out a small window. Ground plane. Usually some variation of the ground plane antenna. Thin steel whip mounted vertically. Vehicle body serves as the ground plane. A full-size vertical is not practical in HF bands. Well, depends on how you mount it. Some type of loading is used to make a short antenna resonant in the desired bands. Okay, mobile HF antennas. The term loading is referred to an antenna. For antenna refers to inserting an inductor in the radiating portion of the antenna to make it electrically longer. So here you've got VHF. Now there's probably 2 HF antennas. And up here you've got 3 elements. Each one has a loading coil. And you wouldn't think that would work, but the radiation pretty much goes in the path of least resistance. So whichever one is tuned, you could actually switch bands inside the RV and use this on 3 different bands without having to go outside and switch it. So radiation is actually going to each one, but the one that's tuned will pick up most of the antenna radiation and
Will
take
it
care of
mess anything up if you have 2 antennas close like that together?
If they're on significantly different frequencies, they won't affect each other.
But if it's close, it will.
Yeah, they will. If they're harmonics, they'll affect each other. He's probably seeing some effect on this antenna just because there's a steel or aluminum mast right there. Any two verticals like that will affect each other. So it's going to detune this one somewhat from if it was in free space, but he's probably either using a screwdriver antenna here where the whole thing can be adjusted, or he's using a tuner inside and he'll take care of it there. So the loaded coil adds inductance, lowers the frequency, narrows the bandwidth, does add a little loss, and can be placed at the bottom, middle, or top of the radiator. It's a little more efficient in the middle or the top, but it's often more convenient to put it at the bottom. So what happens if the antenna is not long enough? Well, you can use a loaded coil, or you could add a capacity hat at the top like this. What you want is something at a wire or a T or a plate at the top that will literally try to take some of that energy and spread it out at the top. It adds capacitance at the resonant frequency, lowers it, and electrically lengthens the physical antenna. It does increase bandwidth and it reduces loss. So it's the way to go. Is that if you can put a capacity hat on a vertical, it's more efficient than using a loaded coil. So a mobile HF antenna, you've got linear loading. Part of the antenna is folded back on itself. That produces both capacitance and inductance. Not commonly used, but it's efficient. Screwdriver antenna. I had one of these on a VW van for years, and it worked very well. This section is a coil that doesn't radiate, but it moves up and down across a connector, usually a spring or a couple of aluminum feelers, and that changes the length of the coil for the antenna. So you can mechanically change the antenna resonance on the fly, and it works very well.
You don't need a tuner with one of those because you're tuning.
This is the tuner,
Yeah.
right? The tuner is at the antenna. So you actually get a little more efficiency that way. These are some of the names of the antennas. High Sierra is out of business now. I think Little Tar Heel is still there, Yaesu, etc. But there's plenty of them on the market. They're getting very expensive. Okay, ground plane, mobile VHF and UHF antennas. Properly mounted at 5/8 wavelength antenna for VHF or UHF offers a lower angle radiation and more gain than a quarter wavelength. So does a half wave. Bigger is better in that sense.
So if you go 5/8, you need a bigger magnet.
A quarter wave will have a signal like this, and it's coming down to the ground, but part of the signal is going up there. Use a half wave or a 5/8, now you're squeezing that signal down closer to the horizon. So it's still omnidirectional, but now you're squeezing that signal closer to the horizon, and you've got more gain. That's ideal to mount it in the center of the vehicle roof, not always practical. So you mount it where it works for you. Random wire antennas are random lengths of wire put up pretty much any way you can, often used for shortwave listening, but if you put it through a tuner, you can make it work for transmit as well. Even though the feed point impedance is unpredictable, if you've got a good tuner, it'll be repeatable, you get back to where you want to be for each band. You just make a chart, write it out, so you know how to set the tuner for each band, you're good. So station equipment is part of the antenna. It may carry significant RF current. What they're talking about is, okay, you got a tuner and you're tuning the antenna to resonance, the transmitter likes it, gets full power out. You're tuning everything past that tuner, not just the antenna. You're tuning the transmission line as well. So everything becomes part of the system. And that means if you've got a long length of transmission line, you've got loss in that line. So if you've got a high SWR that you're tuning out, you still have standing wave ratio coming back down that transmission line, going back and forth in that transmission line, trying to make its way out. It produces heat. If it's really bad, you can feel the heat at certain nodes along that transmission line. That's loss. So with random wires, may carry significant RF current. RF burns from contacting equipment are possible. That usually is when you don't have a good ground. If some of your system isn't grounded, you could definitely get an RF burn. Feed point effects. As you move the feed point of a half-wave dipole from the center towards the ends, the impedance steadily increases. An end-fed half-wave has a very high impedance. Why would we want to use an end-fed? It might be convenient. Maybe you're throwing a wire up out in the wilderness. You're camping. It might be a lot easier to find one support for the end of the wire than have to have two supports. So an end-fed antenna works, but you are going to have to tune out that high impedance.
And you're trying to use a lower band, you gotta have a longer wire, so that makes it more difficult.
Yeah. So the feed point impedance is also affected by height above ground. Below a half wave, it steadily decreases as height increases. And that, we can use this to our advantage. If you've got a small lot and you want to work at 80 meters, an 80 meter full length dipole is 120 feet. Maybe your small lot's not that big, but you get the antenna lower and you realize, wow, I can trim 20 feet off of this and it's still resonant. Now it fits. So maybe that creates an NVIS, a near vertical incident wave, but the antenna is fitting on your lot. So the radiation pattern is affected by high low ground as well. Signals reflect off the ground and combine with direct signals to change the pattern. That can work for you or against you, depending on how high your antenna is. Below a half wavelength, the dipole is nearly omnidirectional with maximum radiation up. Near vertical incident skywave, that's NVIS, near vertical incident skywave. That'll be on the test. Useful on 80 and 40 for communicating close in. What they're talking about close in, it's not local. They're talking about within 300 miles. So from here to Portland, or even Seattle, is considered NVIS. A single hop with the signal going at a high angle and coming back down at a high angle.
And we use that all the time on.
That is the go-to frequency for statewide communication. It'll be 80 meters. 40 during the day, 80 meters after the sun goes down. Radiation pattern is affected by height of the ground, and reflection of the signal off the ground results in signal loss. It depends on how high it is, and loss is less if the wave is horizontally polarized, and vertical antennas have a lower angle of radiation than horizontal. All right, let's stop a second. So, you got a vertical antenna. Remember that lobe is from here down. So, yes, there's a lobe here, but a lot of it is right at the horizon. So, I have a vertical for HF, and I have a horizontal antenna that's just barely above the roof. And that's for HF also, but it's for close in. So when I want to work, 80 meters in the evening from here to Portland, I'm using the horizontal. Occasionally, like early in the morning, 3, 4 in the morning, signals will be coming in on 80 from Japan. I'm not going to work them on that horizontal dipole, but I can hear them on the vertical. I can switch back and forth. It goes away. I can hear everything on the vertical. I switch back to the horizontal, and that signal is gone. I don't hear it at all. And it's because of that pattern of radiation. It works on receive as well as transmit. I can only hear those close-in stations on the horizontal dipole. On the vertical, I've got a path between here and Japan, and I can work it easily. So, a vertical works better, but it's less efficient because it's omnidirectional. That signal's going out in all directions, and unless you've got a really good ground under you, a lot of ground radials, the antenna loses efficiency. Plus, like I mentioned before, you've got your feed point right at the ground level. That's the least efficient place to put it. So you've got trade-offs there. But what I find is that I can hear the signals with that vertical and I can't hear them in the horizontal. Horizontal polarization is normally used for long-distance CW, single sideband, on the VHF and UHF bands. it works better. Everybody's on horizontal.